In this video, we're going to be discussing how we can easily find binomial coefficients when we do binomial expansions. So recall that when we discuss binomial expansions, we're saying that we have some binomial that we're raising to some positive whole number power here. And what we want to do is easily find this expansion without having to go through all of the algebra of doing it. So one thing we can do is tie it back into what we call the binomial theorem. Now in my last video, we explored the patterns that show up when you expand binomials in this way. But in this video, I'm going to kind of point out the fact that when we expand a binomial a plus b in general to the n, okay, so this is some positive whole number power, what we get in general is this, okay? And so without going through a lot of the argument here, I mean, I don't want to take a long time on this, but we say taken to the nth power, we see that our first term here, a, started off with all of this n, and we got no power on this b. But we'd say, well, look at the next term here. We get our a value would be to 1 less than this here, n minus 1, but then b would now be to the 1. Okay, so b got 1 bigger, a got 1 smaller. And we say the next term here, we say, look at the exponent on it. A got 1 small or 2 smaller than the original one, but b is 2 bigger than the original one, which were n and 0 respectively. So in general, we say this is going to keep happening until a has none of the power left and b has all of the power left. Okay, so this is what's happening to our exponents on our values here of a and b. What's out front? Now these coefficients out front, you'll notice that I'm using what is called combination notation. And actually the interesting thing here is we could express this in general as n choosing r, okay? So in this case up here we said it's n choose 0, n choose 1, n choose 2, n choose n, all the way out to there. But essentially what I can point out is this: n is going to be the power that you are raising this binomial to, and that's going to be the key to all of this here. But we say that basically right here, this starting at 0 and going out to n, this is some value that we're going to refer to as some r value. So we say n choose 0 where r is 0, n choose 1 where r is 1. That's our r value right there, okay? So in general, we're going to say that our binomial coefficients are always n choose r. Now the nice thing about this is we have Pascal's triangle. So in terms of finding binomial coefficients, we can always go check out Pascal's triangle, this triangle where I'm just summing these values to get these ones underneath, and saying that these actually represent the binomial coefficients of some binomial to the nth power, where the row on this triangle corresponds to that power, but keeping in mind that the first row actually starts at row 0. So we say n equals 0, row 1, row 2, row 3, row 4, and row 5. Okay, so the intent of this video is going to be, how can I find these in general without having to draw this stinking picture every single time, okay? So what I'm going to do is I'm going to point this out. We say combinations in general are listed as this. We say n choosing r, okay? We can also write n choosing r, which is how you would write this right here, as in this vertical, case that you see here. So this kind of format here, we just interpret this as being n choose r, but the formula for n choosing r is really this thing right here. We say it's n factorial over r factorial times n minus r factorial, okay? So it's going to be ideal to identify in each of these instances what our n and r are in these examples. So let's take a look at this set of examples over here. But we say 8 choose 2. What is this here? So the first thing I want to indicate is this: our n value is 8, and our r value is 2. So if I wanted to find this, first things first, we say it's n choose r, whereas 8 choose 2. We could also list this way. We say 8 choose 2. But we say always is this n factorial. So you'll notice that with combinations, you always start with an n value on top factorial. And then we get this. We say it's r factorial over n minus r factorial. So in this case, our r value is 2. And I get this from right here. We say it's 2. But you notice I get this. I get n minus r factorial. So the interesting thing here is I get, well, n factorial, which was the total amount here, factorial, times 2, or divided by 2 factorial times. Now 8 minus 2, we have to do that first order of operations style. And we say we get this right here. So one thing I want to kind of point out is this. We'd say that these two values down here, r and n minus r, if you were to take the number r and add it to the number n minus r, what you get is this. You get these r's to cancel, and you just get n. So what we're really saying is this: these two numbers in the basement really always have to add up to this top number right here if you're doing combinations. So now simplifying this, the nice thing about it is we could rewrite it. We could say this is really 8 times 7 times 6 factorial all over 2 factorial times 6 factorial, where our 6 factorials, they kick out, and we really get this. We get 8 times 7 over 2 times 1, which, when we reduce this, comes out to be 28, okay? So we would say that this binomial coefficient would equal 28, in this case. So let's check a few more of these out here. We say 10 choosing 3 at a time, which is really the same thing as 10 choosing 3 at a time. So we say our n value is 10. our R value is 3. There's two important values to have in your back pocket. So we're going to say, all right, well, 10 choose 3 would be 10 factorial over 3 factorial, and now I get 10 minus 3 factorial. I'm still showing my work here. What I can tell you, though, is this. The moment I knew this was 10 factorial, I could have just told you, or sorry, this is 10 factorial and this is 3 factorial. We could have just said, well, then this has to be a 7 because the 3 and this have to add up to be the top number if you're doing combinations. So in this case, I get 10 times 9 times 8 times, I'm going to leave it as 7 factorial because the way I'm rewriting it is this way. And you can see that these kick out, and I'm really left with 10 times 9 times 8. And this is important, over 3 times 2 times 1, and I'm not going to write the 1. I don't need to. So we say, well, 3 and 9 cross-reduce, or at least cancel. They share a common factor. And then 2, well, 2 goes into 8 and into 10. I'm more inclined to take it into the 10 because it's the bigger the values that's going to knock that down for me. So I circle things that I have left over. And essentially I get this 15 times 8, which is 120, I think. So we get 120 would be our binomial coefficient there. So a little bit more quickly, I'll work these next two examples with you and then leave the rest for the viewer. But basically, we say 7 choosing 0. What would this be? Well, I'd say, well, n in this case is 7. N is 7. R is 0. Look what we get when you do choosing 0. We say, well, it would be 0 factorial over 7 minus 0 factorial. In other words, we get 7 factorial over 0 factorial, which is 1 times 7 factorial. And these things cancel out and we get perfectly just 1 over 1, or just 1. And then also this 8 choosing 8. If we said that n was 8 and r was 8, what would we get for, binomial coefficient? We would get this. We would get 8 choose 8, which is 8 factorial, over 8 factorial times, well, I'll tell you what, this is going to have to be a 0, and that has to be a 1. So we get something divided by itself, so we really just get 1 again. Okay, so see what you get on these other four.